work at Ocasta, which is a local Brighton company that does digital transformation. And I'm going to do a talk today, the very cut down version of a talk that I did at the Async Brighton meetup last year, called the Nitty Gitty, in which I'm going to try to demystify Git somewhat. So I'm going to assume that everyone here has heard of Git, and most of you have also used it in some form or other. If that's not the case, I apologize. Most developers seem to treat Git a little bit like it's a car. And what I mean by that is they think of it as a sort of complicated, intricate, dangerous piece of machinery, which they will learn enough of to get from A to B. But if anything goes wrong, they'll probably call in for help, and they very rarely look under the hood and see how it actually works. And I think this is a shame because, in my opinion, Git is not a car, it's more like a skateboard, in that there are many complicated, intricate, and dangerous things that you can do with Git, but in terms of what it actually is, it's pretty simple. I'm not going to claim it's as simple as a board with wheels on it, but it is pretty simple. So a lot of people complain that Git is complicated. It's definitely complex. So at the moment, it's running at about 145 commands. So there's a hell of a lot of it. And it is also very confusing. And I think the main reason for that is the way it names things. It does some very weird naming. So just to give you an example, you may have come across the phrase checkout when using Git. So checkout originally was a metaphor as in checking out a book from a library. So back in the 90s, I used to use a thing called Microsoft Visual SourceSafe, which was a version control system back then. And in SourceSafe, you would check out a file, which meant that you were the only person that could work on it, and the file was locked. You were the only one that could change it, and then for anyone else to change it, you'd have to check it back in when you were finished with it. In the same way that when you check a book out of a library, you're the only one that can read it until you return it. Now, Git uses the word checkout for all sorts of things. So you can use checkout to move on to a branch, for example. You can use checkout to start a new branch. You can temporarily move on to a commit in a detached head state, and you can even remove local changes from a file. And these are four very different things, and none of them have anything to do with checking a book out of a library. So it's no wonder that people find Git confusing. So I'm going to try to demystify it a little bit. What I'm going to do first is I'm going to talk about the basics of Git, which hopefully everyone understands, but I will run through it quite quickly. Then I'll talk about the building blocks of Git, what Git actually is under the hood. I'm going to talk a little bit about the branch model, which I think is the part of Git that people find most confusing. And then I'm going to talk a little bit about the history and how you can manipulate it. Let's start with the basics. What is Git? So Git is a version control system, or a VCS, which means it's a bit of software that allows you to keep a history of your project as you go along. It allows you to restore previous versions of the project. It allows you to multitask, so you can have different people working on different versions, and also allows you to collaborate. It's the only sensible way you can collaborate. And this one's interesting. It allows you to document the evolution of your project. And I'm going to talk about that a bit more later. So the basis of Git is the idea of snapshots. So imagine you're building a project, and as you go, you take a snapshot of the project, and then you keep building it, and you keep taking snapshots. And then if at any point something goes wrong, you can use your previous snapshot to get your project back to a sensible state. And in terms of how this works in Git, you have a folder on your machine called the working directory, and that folder contains some sort of project. So as an example, I'm using a simple web project here with an index.html, a CSS folder, and the stars.css in it. Now, if you want to use Git to maintain the history of this project, then you would have a Git repository on your machine that sits next to this directory, and that Git repository would have a copy of that project in it, a snapshot, and it would also contain any history of that project in it as well. In between the working directory and the repository sits a thing called the index. So I've used a shopping basket here because what the index is it's a staging area that lets you collect together your changes, and then when you're ready with them, you can put them into Git, so, into the repository, sorry. So let's say you make a change to index.html. And you want to add it into the index, you would use the command git add, and that would put your change into the index. And then you could do the same thing with a change to styles.css. And then when you're happy with all your changes, you would use the command git commit to add a new snapshot into the Git repository. And you would keep doing this as your project evolves. So let's talk about the building blocks of Git. What is Git under the hood? So Git has an object database in which it stores all its information. And there are 4 types of objects, the 4 wheels of our skateboard. There's a blob, a tree, a ref, and a commit. I've used a picture of a comet there. I'm sorry, that wasn't a very good pun. It was either that or commit the frog. I don't know what you prefer. So let's start with blob. Blob stands for binary long object. You may have used these in your programming before. If you imagine this picture of Mr. Blobby.jpg, when you save it to your computer, what it actually is on the computer is a massive binary number. And this is the actual binary. It's going off the screen, off the bottom. And when Git saves this JPEG inside its database, it saves it as this long binary number. The same is true for a text file. If you've got an index.html, if you look at it in your text editor, you see text. But it's actually also just a big binary number, and this is the binary number for this text file. And Git will store this index.html text file also as a long binary object. When it stores them with a string that looks like this, which is 40 characters of hex. And this string is an SHA hash. SHA is an encryption algorithm that can take some binary data and convert it to a string. And the string depends entirely on the binary data. So if you change the binary data, the string changes completely. And Git will use these hashes as IDs for its objects. So the next type of object is a tree. A tree represents a folder on your project file system. It's also associated with a hash based on its contents. And then it has an entry in it for each file and subfolder within that folder. And each entry will have a name, for example, index.html. It'll have a type, which is either a blob if it's a file or a tree if it's a subfolder. And it'll also have its own SHA hash. So for example, here's our web project, index.html, CSS, and styles.css. If Git was to store this folder, it would store a tree object with a hash, and that tree would contain a blob entry, which is the file entry for index.html, and a tree entry, which is the folder entry for the CSS folder. And this tree object would exist somewhere else in the database, and that would have a single blob entry, which is styles.css, this file. So that's how Git stores a project folder. So the next type is a commit. Now, commit, as I've said before, is just a snapshot of your file system at a certain point in time. Because a tree represents a folder at a certain point in time, all the commit really does is it points to the root tree of your project. And then it adds some metadata to it. So lo and behold, an SHA hash. This is called the commit hash, so you may hear about that sometimes. It also has an author, a committer, and a date, so metadata for who made the commit and when. It has a commit message, which allows you to add some context to why the snapshot was taken. And it also has a reference to the parent commit, so the previous state of the system before you made this snapshot. So to give you an example, let's say we make a change to index.html here, and we were to store that into Git. The first thing that Git would do is it would store a blob for the new version of index.html. Then it would store a new tree for the project root that has this new version in it. Then it would store a commit that points to the new tree. And the commit would look something like this. There's a command you can run in Git to actually see the contents of commits in the database, and it looks a bit like this. It's got a pointer to the tree with the folder. It's got a pointer to the parent commit. It's got the author and committer, and these are dates in a horrible format. And then this is the commit message that gives you some reason why you made this commit. So the final type of object in the database is called a ref. And a ref is just a thing that points to a commit. It's just a reference to a commit. And it gives that commit some sort of meaningful name. Now, there are 2 types of refs, tags and branches. They're very similar. The only difference is that a tag will always stay fixed to a certain commit, whereas a branch will update to the latest commit while you're working on that branch. So, for example, here's a tag. We've got some commits A, then B, then C, then D, and then we've added a branch, version 2, which points to commit D. If I make a new commit and then another commit, the tag version 2 stays exactly where it is. So the tag is pointing to the commit D. Whereas with a branch, I've got the same history, and I've got a branch ref, which points to commit D, and I'm working on this branch. If I add another commit and then another, the my feature ref will move along to the latest commit. So that's the only difference between those two refs. And in terms of data, that's it. Now, obviously, it's not as easy as a skateboard, but all there is in terms of data is a blob, tree, ref, a commit, and a ref. Everything else in Git is commands that manipulate this data. So I'm going to explain a few of the important commands in Git. I'm going to explain the commands to do with the branch model because people often find this confusing. So a branch, like I said, is just something that points to a commit. Because each commit has a parent, that essentially means that a branch represents a linear history. So for example, you have a commit A, you have a commit B, which has a parent of A commit C, which has a parent of B, and a commit D, which has a parent of C, and a my feature ref points to D. Essentially, my feature has a linear history of A, B, C, and D. That's the my feature branch. So branches are really lightweight and disposable. You can make as many as you like, you can delete them, they're very easy to delete. And one of the reasons that Git became popular was because its branching model was really easy as opposed to earlier versions. It was quite hard to make a branch. By default, when you start a Git repository, you have a branch called master. And then to create a branch, you can do git branch my branch. To move on to a branch, you would do git checkout my branch. I'll explain a bit better what that means. And you can do both at the same time if you want to with checkout -b. So what do I mean by on a branch? There's this concept in Git called the head, and the head is essentially a pointer to your current position within the Git repository. What are you currently working on? Now, it normally points to a branch, and when it does, you are said to be checked out onto that branch. That's that phrase again. You're working on that branch. Now, you can actually point directly to a commit, and the only reason I mention that is because you're said to be in a detached head state, which is not as scary as it sounds, I promise you. So let's see this in action. You start a project, git init to start the project, and then you make a commit. And as soon as you've made a commit, Git will have a commit in history, A. It'll have the ref of the master branch, which is the default branch, which points to A. And your head, which represents where you are, is on the master branch. So you're checked out onto the master branch, and the master branch is on commit A. If you then make a new commit, it'll make a new commit B with a parent of A. The master branch has moved to point to commit B, and you are checked out onto the master branch. If I run git commit again, then it's the same story, but for commit C. Now at this point, I might decide that I want to start a new branch. So I could do the command git branch my branch. And what that would do is it would make a new ref called my branch, which points to commit C. I'm not working on it, I've just made it, so the head is still on master. To work on the branch, I would do git checkout my branch, and that would move the head, so it's now pointing to the ref my branch. If you then make a new commit, you're working on my branch, and the new commit has a parent of C, and the my branch ref moves, so it points to commit D. Now notice that master has stayed exactly where it is. So what I said before about the branch refs moving to the latest commit, that they do that if you are checked out onto that branch. But because we're no longer checked out onto master, the master ref stays exactly where it is. You make another commit, and now we're pointing to commit E, and it's the same story. So now at this point, let's say you decide you want to check back out onto the master branch, you would do git checkout master, and the head would now move back to the master branch. And now if you make a commit, you have a new commit F that has a parent of C, and you can do the same. Now you'll notice here that C is the parent for both F and D, and what we essentially have is two parallel histories here. So the commits E and D are on my branch and not on master, and commits G and F are on master and not on my branch. If we look at this from the branch point of view, you've got two parallel histories. One is A, B, C, F, G, which is the master branch, and one is A, B, C, D, E, which is my branch. Now you're probably asking, why on earth would you do this? So the first reason is it lets you multitask. It means that you can have two versions of your project at the same time, and you can work on them independently of each other. It also lets you collaborate. It's the only sensible way that people can collaborate on a project is they work on individual branches and they don't affect each other's work. And it means you can experiment. So if you want to try something dangerous, you can start a branch, try it out, and then if you're not happy with it, remove it. But we can't leave these branches in parallel. At some point, we need the work from one branch to be on another branch. So how can you share work between branches? So this is where merging comes in, git merge. So merging is a way of incorporating changes from one branch into another branch. Now, it's another example of a bad name on Git's part. So when you merge two things, you expect to end up with one thing. For example, if you merge two bits of plasticine, you expect to end up with one bit of plasticine. But when you merge in Git, if you merge branch A into branch B, you still have two branches at the end of it. Branch B has changed, but branch A hasn't. So it should really be called import. It's a way of importing commits from one branch into another branch. So here's the simplest case. Let's say you start with two branches. There's a branch source and a branch destination. And the branch source has D and E, extra commits on it. Destination doesn't have D and E, but all the commits on destination are on source. So in this case, we say that source is ahead of the destination branch, or destination is behind the source branch. Now, in this case, if you were to run git checkout destination and then git merge source, what you're saying is you want the commits that are on source, which are not on destination, to come onto destination. And what Git would do is it would do this. It would add commits D and E onto the destination branch. Now, you notice that the destination branch has changed, but source remains unchanged completely. So when you merge one branch into another, the branch that you merge from doesn't change at all, and you still have two branches at the end of it. Now, Git calls this a fast forward merge, and the reason is if you look at it from Git's point of view, when you start out, you have a destination ref that points to C and a source ref that points to E, and all Git has to do is to fast forward destination so that it also points to E. Well, that's the easy case, but the more complicated case is much more common. So here we've got two branches that have different histories. So source has commits D and E on it, and destination has commits F and G on it. And there are commits which are in your destination branch that are not in your source branch. So source and destination is said to have diverged. The two branches have diverged. The way that Git deals with this is with a thing called a merge commit. So here's our starting point. We've got a destination branch with commits A, B, C, F, G on it, and a source branch with commits A, B, C, D, E on it. Now, let's imagine that D has a change to index.html and E has a change to styles.css in it. And we want to merge source into destination, which means that we want these changes which are on source to be on the destination branch. So if you do git checkout destination first and then git merge source, what Git will do is it'll add a merge commit. And this is a commit that contains all the changes to index.html and styles.css in that commit. And it's added it onto the destination branch. It will also keep a reference to the commit where the changes came from. So the merge commit has two parents. All commits have a single parent apart from merge commits, which are special. One parent points to the branch that you're merging onto. The other parent points to where the information came from in the first place. So just to recap, a merge commit has two parents. One is the branch you're on and one is the source of the information. It'll contain all the diffs that are in the source branch that you don't have in your destination branch. And the source branch at the end of it remains unchanged in the same way as before. So let's talk a bit about the history. So up until now, we've been adding commits to the history of Git. But Git actually allows you to change history in a kind of Doctor Who kind of way. Now, you're probably wondering why you'd want to do that. So there are two ways of looking at your Git history, and they're both perfectly valid, and different companies use different ones. One way is to see your Git history as a record of what you did and when. So you use Git to keep completely safe everything that everyone worked on the project did and when they did it. The other way to look at it is as a story that you are telling about the history of your project. I'll show you what I mean by that. So let's take this styles.css, and let's say you're working on this project and you notice that there's a bug in your styles.css because in IE11 you need flex to have a percentage on it for it to work. So the change that you want to make is this change. Now the question is, how do we document this change? So a typical way people might do it is they might add some kind of comment. IE11 requires a percentage unit. And this is fine, but there's a lot of problems with it. One is that you are referring to the code, you're not actually referring to the change. So the comment doesn't say anything about the percentage specifically, it's just referring to the line below. You end up polluting your code base with loads of comments. And importantly, if anyone changes the line below or changes the comment, then the information is essentially lost. So there is another way of doing it, which is that you commit the change itself, the percentage, and then use the commit message to give information about why that change was made. So here I've used the commit, and I've got loads of space now. So here I've used the commit message to say added unit flex basis, explained it was a bug. I can even put a link to where the bug came from. Now, a commit message can be used to document a change. And this works best if each commit contains one logical change in it. So not necessarily a change to one file, but all the changes to the files in the commit are essentially one change to the system. This is called an atomic commit. And then if you have a logical sequence of atomic commits, you can tell a story of how the code changed and why. So let me give you an example. Here is a pull request, which shows some changes to my index.html project. And here's another pull request with exactly the same changes. It's identical. The only difference between these two pull requests is the branches that we are trying to merge in are different. One's called record and one's called story. And if we look at those two branches, record and story have completely different histories. So record has 3 commits in it with these commit shars and SHA IDs. The story has 3 different commits in it, but they add up to exactly the same changes. So the record branch is me committing my work as I go. So to show you the commits in it, the first commit is I've made some changes to index. And then the second commit is I've made some changes to styles.css. And then the third commit is some fixes. So I put padding instead of padding, put padding top instead of padding, and there was a typo in my footer. The story branch is exactly the same changes, but I've rewritten the history so it tells a story. So the first commit is adding a footer. It's got all the changes to add the footer in the HTML and add the footer in the CSS. Then the second commit is inlining an SVG. So I've got an image that was originally an SVG file, and now I've put it in line. And the third commit is changes needed to add a container and styles for the logo. So a Git history that tells a coherent story, like I showed you, has some advantages to it. One is that it allows you to document the reasons for the changes. Another is it can make it a lot easier to do code reviews. So rather than having to review a big wall of changes that are all added together, you can review the individual commits and see the reasoning for the developer making each change. It also allows you to search the history to help you fix bugs. So someone who's found a bug in the system and who wants to know why a certain line has changed can use the Git history to find out where that change happened. The problem is that the process of coding is messy. So as you code, you change lots of things at the same time. And if you just commit as you go, it's quite hard to tell a story. So you can use Git commands to refactor your history and then tell the story of your project. So let's talk about some commands that allow you to change your history. The first one's git commit -- amend. So amending a commit. It's exactly the same process as commit, except instead of adding a new commit, it adds changes to the current commit. So you can also, if you want to, edit the commit message. So here's a commit history, A, B, C, and D. And let's say D has a change to index.html, and in my local file system, I've got a change to styles.css. I can use git commit - amend to amend commit D and add styles.css change into commit D. Now I've put D prime here because this is not the same commit D. This is a brand new commit, and it's got a brand new SHA hash. Because it's got different changes in it, it's a completely different snapshot. It's got the same commit message, but it's a completely new snapshot. So that's how you amend a commit. Another one is git reset. So git reset is the opposite process to commit. It's essentially uncommitting. It allows you to remove all the commits up to and including the target. And then any diffs that are in those removed commits become local changes. So here's an example. We've got a history of A, B, C, and D. And then let's say C has changes to index.html and D has changes to styles.css in it. If I reset to commit B using the command git reset, what Git will do is it'll do this. It'll wipe those two commits, and it'll take these local changes to index.html and styles.css, and it'll turn them into local changes, which you can then do whatever you like with. You can make a new commit out of them, you can move them somewhere else. And the final one is git rebase. A lot of people are quite scared of this command, but it's really useful and it's really interesting. It allows you to change the starting point or the base of a sequence of commits. And what it does is it will say, rewind the commits to the current starting point and then reapply those commits from the new starting point. Now, I'll have to show you what I mean by this because it's a bit complicated. Here is our starting point. We have a branch master, ABC, off of which became a branch 1. So the branch 1 goes A, B, C, F, G. So the base of branch 1 is C, but then master has some extra commits on it, D and E. So my original starting point, my original base is C. And what I want to do is I want to change my branch as if instead it comes off the end of master. So the new base is E. So if I were to run git checkout branch 1 and then git rebase master, what I'm saying is I want to move F and G so they're on the end of master. So git will rewind commits F and G, and then it will reapply F and G on top of master, and we end up with this. Now you'll notice I put F prime and G prime. They're the same commits with the same diffs in and the same commit messages, but they have brand new SHAs because they're coming off a different point. So the snapshots are completely different. So these are two completely new commits, but they're now coming off master and they have the same changes in as before. So why on earth would you do this? It looks quite complicated. Well, it's really useful for keeping a clean history shape, and it makes it easier to understand the history when you look at it. So let's take an example. You've started a feature which comes off the branch master, and then while you're working on that feature, someone has added some bug fixes to the master branch, and you want those bug fixes in the branch that you're working on the feature branch. So the typical way you might do this is you would merge those changes into your branch, and then you might make some more changes, and then when your branch is ready, you would merge your feature branch back into master. And it's a perfectly sensible way of doing it. It's the way that we insist people do it at my company. But as you can see, it's a bit confusing to work out what's actually going on here. So there is another approach. Instead, what you can do is when you're at this point and someone's added some new commits onto master, instead of merging in, you can rebase your branch off the end of master, then make the changes that you want, and then merge your changes back into master. And now you can see that the history is a lot easier to understand what's going on. These changes were made, then these changes were merged in. And you can see how this is useful if you look at when there's lots of branches going on. So here is just two feature branches that merge in some changes from master and then get merged back into master. A lot easier to see is if they rebase instead. And then you get this lovely history where you've just got the history up until E, then the next branch comes in because that was rebased off E, and then the next branch comes in. These are called camel humps. So that's kind of all I've got time for. I've tried to get this down to half an hour. Sorry if it went a bit fast. There's a lot of stuff I didn't get a chance to talk about. I didn't talk about remotes, so Git push and pull and how to share work between different machines or with GitHub. I didn't get a chance to talk about conflicts, so what happens when you merge but the merges aren't compatible with each other and how you fix that. Or workflows, so things like git flow, having a develop branch, a feature branch. And there's loads of useful commands that are worth looking up to find out more. Git cherry pick is a way of getting any commit you like onto your branch. Git stash is a way of storing your local changes for safekeeping while you move around. Git revert is a way of, instead of removing a commit, you add a commit that does the inverse, so you undo a commit by adding a new commit. Git reflog is a history of everywhere that you've been in Git up until now, which makes it very easy to fix a mistake. Git blame, or annotate as people like to call it instead, where you can see for a single file what commit changed each line in the file. And git log -s, which is called the pickaxe command, which allows you to search your Git history for a string. So I'd recommend, if you're interested, to look up some of these things. There's a couple of useful links. Most of the information from this talk came from ProGit, which is the official Git book, essentially, and it's available for free on that link. The Atlassian, who make Jira and Bitbucket, have some Git tutorials on atlassian.com/git, which have some really nice diagrams in and are quite easy to follow. I'd recommend them. There's actually a command line tutorial. So if you run git help tutorial in your command line, it'll run you through a Git tutorial. And there's two of them. And the second one goes through all the stuff I was talking about with blobs and trees, etc. And apologize for the swearing, but there's a site called ohshitgit.com, which is a site where if something's gone horribly wrong, it's got examples of all the stuff that typically goes horribly wrong and how you get out of that situation. And that's it for me. Thank you very much for listening. And I'm very happy to answer any questions if I can.
That's brilliant.